For many students, the early applications of integration involve finding the area bounded by a curve and the x-axis. What we're going to do in this particular section is we're going to look at the problem of solving areas bounded by two different curves. So here the curves I'm looking at are y equals 2 to the x, which is the one that's concave up here, and y equals 10 minus, oh my goodness, 2 to the 4 minus x, which is this one that's concave down. I'm going to make a couple little comments here. First of all, I'm going to note that they intersect at the points 1, 2, and at the point 3, 8, which can be confirmed by substituting 1 into each function and obtaining 2, and substituting 3 into each function, obtaining 8. Our old problem was not finding the area bounded by two curves, but finding the area beneath a given curve. So let's just look, for example, at the area bounded by that curve g of x and the x-axis on the interval from 1 to 3. Well, if we do that, we get something that would look like this. The region bounded by those two curves on that interval, forgive my coloring outside the lines there, but it would look something like that region there. And all we would have to do there is find the integral from 1 to 3 of that 10 minus 2 to the 4 minus x dx. Now the problem there is we end up with too much region. And so what we can do is we can eliminate the overshoot, and by taking the region bounded by the other curve in the x-axis and subtracting that from the value that we just calculated. So when we do that, we would subtract the integral, we would subtract the integral from 1 to 3 of 2 to the x dx. So in all, we would end up with an integral from 1 to 3 of 10 minus 2 to the 4 minus x, and because the limits are the same from 1 to 3, we could subtract 2 to the x and then dx there. Now, I have drawn here a nice little, if I do say so myself, a nice little rectangle. Okay, what is this rectangle representing? Well, this rectangle represents an approximation of the area of the region that I'm trying to find. In fact, it represents, for example, the thickness, which we would call delta x, multiplied by the height of that, and the height of that, because the top function is y equals 10 minus 2 to the 4 minus x, and the bottom function represents y equals 2 to the x, this rectangle would have height equal to 10 minus 2 to the 4 minus x minus 2 to the x for some particular x value down here. So we can see that this rectangle is given essentially, in effect, kind of, I'm really committing to that, aren't I? By this product of the height of the rectangle kind of multiplied by the width there. Okay, so the big problem in this particular section is setting up the integrals. Evaluating them is often not too terribly difficult. We don't typically have to do some of the more advanced integration techniques. So in this particular case, I'll just go ahead and say, well, the 10, let's change back to black here. The 10 will be 10x. I'm going to skip the middle one for a moment. I like skipping these things. I'll put a minus there for a placeholder. And then the 2 to the x, well, let's see. The antiderivative of a to the x dx, the derivative of a to the x is a to the x times the natural log of a. So the antiderivative is 1 over the natural log of a multiplied by a to the x. And then we could put a constant there if we want to. So the 2 to the x is going to be 1 over the natural log of 2 times 2 to the x. Okay, this guy in the middle, it's another exponential function. So we would have the same sort of business. We would have 2 to the 4 minus x. I have to do the 1 over the natural log of 2. And then You could use substitution. I'm kind of foregoing that. But what you can do is you can say, what is the exponent? The exponent is linear. The derivative of that exponent is -1. So in order to compensate for that -1, we would divide by -1, which would change that to a plus instead. Again, you can always resort to substitution. Now, we won't need to evaluate this from 1 to 3. And some calculations shows us that the total area bounded by these two curves is 20 minus 12 divided by the natural log of 2. You can pause it and kind of look through the calculations there. In general, what we did was we took the function that was on top, we subtracted the function that was on bottom to get a measurement of the distance between those two curves. We multiplied that by dx to essentially think about the width of that rectangle. Let's look at another example here, or let's look at some problem-solving strategies first. So here's how you're going to have to do these. You have to graph it. You can't just imagine it in your head or take a guess as to which function is larger and when they'll intersect. You have to graph them. If you need to, and you're permitted to, use a calculator to do that. That's fine. But you should also draw them on the paper. It's very helpful to shade the region of the area that you're trying to find. Determine where the graphs intersect. Often that can be done just by inspection, but you might want to verify through substitution that that's where they intersect. And maybe draw several rectangles. Sometimes it's helpful to do the rectangles that we just saw a moment ago, where you've got skinny ones that are tall but skinny horizontally. Or we might want to switch integration, and we'll do the first example in two ways. We might want to switch integration so that we integrate with respect to y, and the rectangles that we draw are skinny in the y direction, which means they're not very tall, but very long instead. If you're stuck on how to integrate a particular area that you've set up, well, maybe you want to go ahead and make that switch that we discussed just a moment ago. One thing you've got to be very careful about that students tend to make a mistake with, ignore the axes. They are not automatically part of your boundaries. I think it's helpful to draw stuff in a different color and then make sure that you're only looking at the regions between the colored curves that you have. So let's look at our first example. We want the area of the region bounded by the curves y equals x cubed and y equals the square root of x. I'm going to go ahead and graph these. And here are our graphs. Now, one strategy that I like to employ, but it's not always perfect, is if the functions are given to you where you have y is a function of x. Here, y is x cubed. Y is a function of x. Y is x squared, or the square root of x. I like to think about having skinny rectangles where they're skinny in the x direction. So I'm going to draw a couple of little rectangles, something like so, and something like so. And I want to imagine that if I take one of these rectangles so that one of the top of the rectangle is on one of the curves and the bottom one is on the other, if I move it across and they stay on their respective curves, do the curves ever switch? Well, the top of the rectangle appears to always be on the red curve. The bottom of the rectangle always appears to be on the blue curve. And so it seems like I'm in good shape to do what I'm about to do with this area problem. We're going to take, let's see, which one is on top? The top one is the square root of x. I notice that I have the intersection points of 0, 0, and 1, 1. So that means x varies between 0 and 1. Those will be my limits of integration. So the way we like to do this is we like to say, well, it's going to be the integral from 0 to 1. And then we're going to do the one that's on top minus the one that's on bottom. What do we mean top and bottom? And we've got to be careful. The only reason I'm choosing top and bottom is because I'm integrating with respect to x. Okay? In the next example, we're going to do this all over again. And then when we do it over again, it's not going to be the top one minus the bottom. We're going to do something slightly different. Here, the top one is the square root of x function, and the bottom one is x cubed. Now, it might seem kind of strange because you think you would put the larger one on top. Isn't the square root function less than x cubed? It is when we're past 1, but when we're between 0 and 1, they're actually flip-flopped. So we're going to look at the integral from 0 to 1, put it in an integrable form, x to the 1/2 minus x to the 3rd dx. And we go ahead and we integrate. Add 1 to the exponent, we end up with x to the 3/2, multiply by its reciprocal out front, 2/3, minus 1/4 x to the 4th, evaluated from 0 to 1. When we substitute in 1, we'll get 2/3 times 1 to the 3/2, minus 1/4 times 1 to the 4th. And then when we substitute 0 in, don't automatically assume it's 0, but in this case I have 0 to the 3/2, which is 0, and 1/4 to the 0th, which is 0. Don't assume that, especially if there's a cosine or an e to the x involved. Those will mess you up. So we end up with 2/3 minus 1/4. If we put that in terms of twelfths, that's 8/12 minus 3/12. So we have an area of 5/12. And that seems kind of reasonable. 5/12 is less than 6/12, which is a half. We are confined to a 1 by 1 square, but we of course don't have it all. So that seems like a reasonable one to do. Okay, let's start this problem all over again. This time what I'm going to do is I'm going to do the same area, but I'm going to treat the rectangles as if we're only looking at small changes in y this time. Okay, so wait a minute, what do we mean by small changes in y? Well, if I have a small change in y, I'm looking at a small distance here. And so what we'll do is we'll construct a rectangle going sideways this time. And the thickness of that rectangle, you should think about, well, it's only a small change in y. You could think about it as delta y. Some people write dy. I'll be a purist today. I'll just write delta y there. We could do the same thing down here. And the same thing up here. Now let's look at the boundaries of each of those rectangles. The bottom rectangle, on the left, the boundary is the red curve. On the right, the boundary is the blue curve. The same thing is true for the second highest rectangle as well as the one that's up the highest. So it seems to me like we've got the blue one on the right and the red one on the left. Okay, now here's the thing. If I'm going to do delta y, that means when I go to my integral, I'm going to do something with dy, which means I have to be in terms of y. Okay, what we'll be looking at this time is not the change up and down for the height of the rectangle. The height of each rectangle this time is this dy that's hanging out at the back end. Instead, we'll be wanting to calculate this distance, which is the distance between the two curves left to right. Again, those are the distance between the two curves left to right. Now, if I'm moving left and right, but staying at the same height, my x value is changing, which means I need to take each of these equations and solve them for x. So this would say that x is the cube root of y, or y to the 1/3. And then for the other function, it's going to look prettier than that. We would have x equals y squared. Okay? Now, let's think about this. If I'm moving left and right, where will my x value be larger? Will it be larger on the left, or will it be larger on the right? Well, of course, it's going to be larger on the right. So what we'll do in these circumstances is we'll do the integral. Let's change that back to black here. The integral of the rightmost function minus the leftmost function. That's weird because before we did the square root function, the red one minus the blue one. Now we're doing the blue one minus the red one, and that's because we're doing the rightmost minus the leftmost. Okay? Now we also have to be careful. If we didn't catch this, it wouldn't matter in terms of our final answer, except we would have done the problem incorrectly, yet gotten the correct answer. Here, my y value starts at 0, and my y value ends at 1. So my limits of integration have to be in terms of y, y goes from 0 to 1. So we'll have the integral from 0 to 1. My rightmost function is y to the 1/3. My leftmost function is y squared dy. When we do our integral, we'll have y to the 4/3. We have to multiply that by 3/4 out front to compensate for the exponent when we bring it down, minus 1/3 of y to the 3rd power, evaluated from 0 to 1. When we substitute in 1, I'm going to do some shortcuts here. 1 to any power is 1, so we'll just end up with 3/4 minus 1/3. 0 to any power, whether it's the 4/3 power or the 3rd power, is going to be 0, so that's not going to contribute anything. We end up with 9/12 minus 4/12, which once again is 5/12. So of course we should get the same answer if it represents the same area. So we see that we can sometimes do the integrals with respect to x, in which case we have rectangles that are tall and skinny. Sometimes we'll do it with respect to y, in which case I don't want to call them short and fat, but that's kind of what they are. Okay, for our next example, we want the area of the region bounded by x plus 4 equals y squared and y equals x plus 2. Now this one's a bit deceiving in my mind because the second function is written in terms where y is a function of x. Here's an x value. You should be able to plug it in right away and get the y value. The first equation is not so much. If I plug in x, well, I can get y squared really quickly by adding 4. If I plug in y, it's a little tricky because, it's tricky because if I plug in y, then x, I'd have to take 4 from the other side. Okay, so we've got to make some decisions. Should I solve each of these explicitly for y, like this second one is? Well, this one, if I did that, I would have to get y equals, I'd have to take the square root. When you introduce a square root, you got to do both the positive and negative square roots. That seems like a little bit too much trouble for me. On the other hand, I could solve them each for x. If I solve them for x, I would get x equals y minus 2. Pretty easy to recover x from y there. Here I would get x equals y squared minus 4. If you give me a y value, I can give you an x value pretty quickly. So I think solving each of these for x is a good idea. Let's do that. X equals y squared minus 4, and x equals y minus 2. And let's graph these. Here is the graph of these two functions together. Now, once again, I've colored them in red and in blue so that we don't get the axes confused with one of our boundaries. I want the region that's bounded by these two curves. Now I have lots of different regions. I've got this region out here, which is unbounded because it keeps on going. You want to imagine having the Microsoft Paint option where you've got the paint bucket or some other paint thing. If you drop a bucket here, empty the bucket here, it has no boundaries. If you empty it down here, it would just extend all that way. But if you empty it in this region, it's going to be stuck by the red curve in this area, and then it's going to be, and then it will be confined by the blue curve right here. So the region in question is this region right here. Okay, so I'm going to make an attempt, and it's going to be a bad attempt here. I'm going to make an attempt by saying, let's do a rectangle that goes up and down. And I just did that in green. That's okay, you can see green. I did that in green. So there's a rectangle that goes up and down. The rectangle that I just drew on top is red, and on the bottom is blue. The bottom curve is the blue curve, the top curve is the red curve. On the other hand, when I move over here, as I move those rectangles to the left, the top curve is still the red curve, but now the bottom curve is also the red curve. So when we hit this point -3, we switch which curve is on bottom. We go from the red one before -3 to the blue one after -3. That's not necessarily a deal breaker, but what it would mean is that we would have to do two separate integrals, and I don't like to do two separate integrals. So I'm going to erase those two rectangles. I might have to do some redrawing here, but that's okay. And instead what we'll do is we will take rectangles that are going to be skinny in the y direction, and so they'll move kind of left to right instead. So we're going to have a rectangle here. Draw that guy in, draw this guy in. You should think about more, but I'm just going to draw these two as good examples. Notice that as we move up and down, on this one, the rightmost curve is the blue curve, the leftmost curve is the red curve. On this one, the rightmost curve is the blue curve, the leftmost curve is the red curve. As the rectangles would move up and down, we would still have that throughout the entire interval. We need to establish our limits of integration. Our limits of integration will be defined by the ordered pairs the intersecting points. This one intersects at -3, -1. Up here, we intersect at the point 0, 2. Now, our rectangles are skinny in the y direction. We'll call that delta y. As we have it set up, we have it solved for x up here. So we'll multiply whatever we come up with by dy as the essentially representing the thickness of these rectangles. Once again, we want to start from the rightmost curve. The rightmost curve is the blue curve. The blue curve here is the line, which is y minus 2. We're going to go to the leftmost curve, which is the parabola, which is x equals y squared minus 4. So remember, we're doing the rightmost curve minus the leftmost curve, because if you take 2 points that are at the same height, the point that's on the right will have the larger x value. When we want to find the distance between 2 points, we take the larger x value minus the smaller one. So, because I'm integrating with respect to y, it is the y coordinates that we're most concerned about in terms of the integral. Okay? So I notice that y varies between -1 and 2. So those will be my limits of integration. A common error is to say it's from -3 to 0, or maybe even -4 to 0. Remember, we're integrating with respect to y, so my limits have to be in terms of y. So we're going to go from -1 to 2. We're going to do the rightmost function. We decided that the rightmost function was y minus 2. And we're going to subtract the leftmost function, which is the y squared minus 4. And then multiply it by dy. Make sure you put those parentheses in here, because the negative will end up distributing to that minus 4 there. So let's simplify. And when I say simplify, it means we've got to actually have a couple of steps here. Integral from -1 to 2. We'll have y minus 2 minus y squared, and that'll be plus 4 dy, which is the integral from -1 to 2 of y plus 2 minus y squared dy. Okay? It's very helpful, for your sake, to combine like terms whenever you can. -2 plus 4 gives us the positive 2 that's there. Again, it will work if you don't, but it saves you time if you do simplify. So we're going to find the antiderivative. We'll get 1/2 of y squared plus 2 times y minus 1/3 y cubed, evaluated from -1 to 2. Which, after we calculate everything, becomes 9/2. Again, if you want to see the calculations, pause the video for a moment and look through them to verify that you understand where they're coming from. For our last example, we're going to do something that's pretty complicated because it's got 3 different functions that will serve as our boundaries. So let me go ahead and draw these 3 functions. So here we have 2 linear functions, y equals 2x and y equals 1/4 x, and this bizarre power function 2 over x squared, which is really shrinks quickly as x gets very large. Now, once again, we want the region that's bounded by these curves. There, once again, are lots of regions we can discuss. We could discuss this region out here, but it's not bounded. It keeps going on out forever. We have this region, which has all three curves intersecting it, but it's unbounded as we move out this way. The region that we're looking for is this region in here. Okay, so that's the area that we're going to try to find. Okay, so once again, we want to think about the different kinds of rectangles that we can do. Okay, I'm going to try vertical rectangles. We're going to see how much we like that. If I don't like that, I'll try horizontal rectangles, ones that are short and fat. And if we don't like that, then we're going to revert to what we have. I'm tempted that because everything is y as a function of x, I'm tempted to just say we're going to do it in terms of x. But let's check it out. So let's draw some rectangles. Got a rectangle there. There's another nice little rectangle. I've got a rectangle here, and suddenly I have a funny feeling because all of the rectangles that I'm drawing have a bottom boundary of the blue curve, the 1/4 x, but suddenly at x equals 1, we have this switch between the top curves. Before that particular point, we have the red curve that's on top. After that point, we have the yellow curve. Okay, while I'm at it, let me go ahead and label these points. This is the point 1, 1. This point, through some experimentation, is 2, 1/2. What do I mean by some experimentation? It's where the blue curve, 1/4 x, intersects the power function 2 over x squared. When x is equal to 2, we get 1/4 of 2, which is 1/2. For the other one, we would get 2 divided by 2 squared, which is also 1/2. So that's what that intersection point is. And the other important intersection point is the origin, 0, 0. Now, I want you to take a moment, pause the video, and think about if it's worthwhile to do it with respect to y instead. What I hope you've discovered is that it is not worth it to switch to write this in terms of y, because these skinny rectangles in the y direction will sometimes have the yellow curve as the right boundary, and sometimes they'll have the blue curve as the right boundary. So we'd have to switch anyhow. So we're going to do this sticking with x, but we're going to have to set up two different integrals. One of our integrals will be on the interval from 0 to 1, and the other one will be from 1 to 2. Because of this splitting point where we switch from the red curve being on top to the yellow curve being on top. So from 0 to 1, we'll do the top curve, which is the red curve. The red curve is y equals 2x minus the bottom curve. The bottom curve is 1/4 x. Okay, I can handle that. dx. And then that's the first region. And then the area of the second region is going to be the integral from 1 to 2 of the top curve, which is the crazy 2 over x squared, which I'm going to write as 2x to the negative 2, minus the bottom curve, 1/4 x dx. Okay, so we can do some simplification. First of all, the first one, both are linear. 2x minus 1/4 x, we can combine those values. 2 minus 1/4 is 7/4. And then this other one, we're just going to go ahead and evaluate. If I add 1 to negative 2, I get negative 1. Divide by negative 1 is just going to change the sign of things. 2x to the negative 1. Minus, when I add 1 to this exponent, I'll end up with x squared. I have to multiply by 1/2, so it's going to become 1/8 x squared, evaluated from 1 to 2. Over here, this 7/4, when I take the antiderivative, becomes 7/8 x squared, evaluated from 0 to 1. And now we'll evaluate the stuff on the inside. It's going to become, let's see, negative 2 x to the negative 1 is like 1 over x, so that's times 1 over 2, minus 1/8 of 2 squared. And then we have to subtract the whole quantity. When I put 1 in, I'll have negative 2 times 1 to the negative 1, which is 1 over 1, minus 1/8 of 1 squared. When I substitute 1 and 0 in, I end up with 7/8 times 1 squared, which is just 1, minus 7/8 times 0. And this mess becomes 3/2 when all is said and done. Is that a reasonable answer? Well, let's see about that. This whole region is trapped between, inside I should say, a rectangle that's 2 by 2, so really a square that's 2 by 2. 3/2 is 1.5. 1.5, that seems rather reasonable, because half of the square would be area 2, and we have a little bit of a dip because of the yellow curve here. So it looks like, yeah, maybe we did lose half overall.